Welcome back, everyone, to our last week of new material. Next week will be review. So the culmination of this week is Test 6. And Test 6 covers just 2 sections, which put together everything we've done so far. So those sections are 4.1 and 4.2. The test for this material will be on Friday, November 13th. All right, so let's get started with what this chapter is all about. And this chapter is all about points where a graph has a horizontal tangent line. That is, these points we've been finding in a bunch of the examples for a couple weeks now, where the derivative is 0. And I want to talk about what the shape of the graph is at such a point. And really, if you think about it, there's sort of 4 things a graph can look like if it has a horizontal tangent line. So it can look like this, where at this point there's a horizontal tangent line. It can look like this, where at this point there's a horizontal tangent line. Or the ones we see a little less often, it can look like that. Or it can look like that. And we're going to give names to each of these shapes. So these 2 I'm just going to call a kink in the graph. This I'm going to call a local min, for reasons that I will articulate in a second. And this I will call a local max. Why am I calling this a local max? I'm calling it a local max because the value of this function is the biggest here, at least of nearby points. Maybe the graph does something like spike over here and it's not actually bigger, but as far as points nearby this point, this is the biggest value. Hence the maximum. Likewise here, except for the minimum, this value is smaller than all of the values nearby. For applications, particularly in economics and business, usually whenever you're given a function, you're either trying to minimize it or maximize it. Trying to minimize the cost while maximizing the profit, for example. These things show up a lot throughout our lives. So, really this chapter is about 2 special things that can happen at these points. The first special thing that can happen is that you can find the maximum or minimum value of a function. And when we talk about section 4.1, that's exactly what we're going to be doing. The second thing that can happen at one of these points is that the graph can change direction. That is, it can change from increasing to decreasing, or from decreasing to increasing. This second observation is going to allow us to determine, just from an equation for a function, where the function's increasing and where it's decreasing. And that's the second thing we're going to do in this chapter. But both of the sections, 1 and 2 of this chapter, are going to hinge entirely around these points, okay, where the derivative is 0. So we're going to give a name to these points, namely a point xy on the graph of f of x, where f prime of x is equal to 0, is called a critical point. So if I say critical point, I'm talking about the pair of both of them. If I want to refer to the x coordinate only, I'll call that a critical number. And if I want to refer to the y-coordinate of a critical point, that is the output, I will call that the critical value. So going back to this previous page, basically what I'm telling you is that if you look at the graph of a function at a critical point, it's going to look like one of these 4 things. It's either going to look like a local max, or a local min, or it's going to look like one of these 2 flavors of kink in the graph. I'll go ahead and point out, if you look at the 2 things we're interested in, which are maxes and mins, and where the function changes from increasing to decreasing or decreasing to increasing, Neither of those things are going to happen at one of these kinks. So by and large, what we're really going to be interested in is places where the graph looks like one of these two things. And those places are going to hold the key for both of these two kinds of problems. To emphasize the vocabulary here, let's just do an example where we write down what the critical numbers, critical values, and critical points are of this particular function. So they're all supposed to correspond to places where the derivative is 0. So to start this question, I have to take the derivative here, and I have to solve that being equal to 0. And that will give me two things, x equals minus 2 and x equals plus 1. These x's, the inputs where the derivative is 0, these are what we call the critical numbers. So when I talk about finding the critical numbers, all I'm saying is take the derivative, set it equal to 0, and solve that list of x's that you get. That's your critical numbers. Now, as we've gotten used to, each of these inputs also has a matching output on the original function. And if we calculate that output, we get 2 plus 3 minus 12 plus 1. We get minus 6 for this. And if we do the same thing at minus 2, we get 45. These two things that we got by taking our critical numbers and plugging them in the function to give us these coordinate pairs of points, these are called our critical points. Then we'll also sometimes care about the y-coordinates of these critical points, and those are what are called our critical values. And the values in particular are outputs of the function. Okay, so the critical numbers are inputs, the critical values are outputs, the critical points are both. I'm going to let this introductory video be a little short, and I'm going to pick up in the next video, and I'm going to start talking about 4.1, where we can start talking about how we can apply these concepts to answer questions about finding the maximum and minimum values of functions. But that's all for this video. I'll see you next time.